So let us start today's discussion. So far we have been looking at 5-4 theory, but today what we shall do is, as I mentioned earlier, that uh, in order to describe how particles are interacting among themselves, we need to know how particles move in space-time. So what we have, so in spirit of this philosophy, what we had done earlier was to look at the propagator of scalar fields, of real scalar fields and complex scalar fields. Today, what we shall do is we shall look at the propagator of fermionic fields or Dirac fields, because this is the basic ingredient that is required to describe interactions in which fermionic particles are involved. So once again, our procedure is the same as earlier. What we shall do is we shall look at the Dirac equation. We know this is the Dirac equation. We shall take the Dirac equation in the presence of the source. So this is our starting point to look into the theory of how the fermionic particles or Dirac particles move in space-time. So we want to look at the propagator for Dirac fields, and this is a non-homogeneous differential equation, partial differential equation, and the standard technique to solve this differential non-homogeneous partial differential equation is to write down the Green's function. You can put a sign, minus sign here, or you cannot, or you may sign, it doesn't matter. So, as I mentioned, any function that satisfies the differential equation of this form is said to be the Green's function of this operator. In this case, this is the Dirac operator. And our aim is to find this function. So what we shall do, once again, the standard procedure is to take the Fourier transform of this function. So we take this function and Fourier transform it. So if I Fourier transform this thing, now I act this function, this function s of x minus x prime with this operator on both sides. So if you do it, what we shall get is the following: I f slash minus m s x minus x prime. So this operator will act only on this part and not on this part, because this is only a function of momentum, and you should remember that this del slash is nothing but the Feynman slash notation. This means that this is this. Now mu del mu, and this del mu, it acts only on the x part, not on x prime. So now this operator acts on this part, and we get v equal to 5 2 pi 4 x of p, and when this operator acts on that exponential, I will get a minus IP, minus, and this I will give us a plus. So what we shall have is p slash m. This is what we shall get. Where p slash is once again down mu p mu. Now if I compare this thing with the delta function, we can write it down. This has the representation, column integral representation. So this implies that this is basically equal to this, and this immediately leads to the condition that ST is equal to And once we have this, you can also write this in the following way. So multiply this by p slash plus n, both the numerator and denominator. This leads us to the following. This is then equal to p slash minus n, p slash plus n. Let us, you know that p slash square is basically equal to p square, right? You can show it easily by using the gamma matrix algebra. Just write down this is gamma mu, p mu, gamma nu, p mu, and then use the gamma matrix algebra. You will get this, right? So if you just multiply, we find that this leads to p square minus n square. Because the cross terms will cancel. The cross terms are m p slash with the minus sign and m p slash with the plus sign. So they will cancel each other. So you will ultimately get this. And from here, you can immediately, this implies that this SP, if you just expand this, you will see that this gives us poles at plus minus EP. What is EP? EP is basically P vector square. This is the 4 vector P, right? This contains P0 and P vector, Pi. And this EP is basically square root of P vector square or Pi square plus M square. This. I'm still for English. Sure. So you can immediately see that. Okay, just one single announcement. Those who have already arrived here in the center, if you feel like possibly maybe 2 or 3 of you can come and attend. So you can immediately see that the poles of this are at P0 is equal to plus minus E plus, plus minus EP, where EP is basically given by square root of E vector square. So you see that the same problem arises here also. You have the same problem of this function having poles at these points, just as we had in the case of the real scalar field propagator. Now, once we see that these are the poles, and the problem is that when you insert, so let me just write down the function x minus x prime. S minus x prime will be equal to d4 d by 5 4. SP is now e slash plus m by p square minus n square. So we can see from here that this propagator, therefore, or this Green's function, as we say, this propagator has poles at p0 is equal to plus minus EP. This integration is d4p, and therefore you can see that you can write it down as p0 d2p. So it basically tells that when you try to integrate the p0, there are poles on the real p0 axis. Because at p0 is equal to plus minus p, so these are points on the real p0 axis. This integrand diverges. So this implies that there are poles. So let me go to the other side of the board. So what we shall do is once again employ Feynman's epsilon prescription. So we shall say that this was SP, but now we shall say that let us construct another function SFP which which is nothing but T slash plus n divided by T slash minus n plus I epsilon, where epsilon is a very small positive number. Okay. So this is the standard Feynman epsilon prescription. That we had also employed in the case of propagators for real scalar fields. So if you say that this is my and this is for the Feynman Green's function in momentum space, I'm not writing in momentum space. So therefore, if this is SFP, so now you can write down SF x minus x prime as integral for p by 2 pi for 4 p slash plus n by p square minus n square plus I epsilon I. So as I mentioned earlier also, this is a long way, this is p square minus n square plus I epsilon. This is basically, write this as p slash minus n I. This will be just a correction, p square minus n square plus I epsilon. So what does the Feynman epsilon prescription do? As we have already encountered earlier also, it basically shifts these poles from the real P naught axis. So now the poles are no longer at P0 is equal to plus minus EP, but rather they are shifted. You just calculate the poles from this expression, you will see that the poles are shifted. And therefore that is the Feynman Green's function. And for that the contour is different and you will get a different Green's function. So this is the result. You can try and integrate this expression, which is not required. We shall not do it now. But you can see that you can write this in a very nice way. This expression can be written as I del slash plus m integral d4p by 2 pi by 4 slash slash 2 power minus I is divided by and therefore this is equal to this, and this we have already encountered earlier. This is nothing but the Green's function, Feynman Green's function for the real scalar. Therefore, we can now see a nice relation between the two. We don't need to calculate the P0 integral using this expression from scratch. We don't need to do that. What we can do is, what we have shown basically is that the Feynman Green's function is basically equal to this real scalar field Green's function, on which this Dirac operator with a plus sign now, I del slash plus n, this operator is active. And we have already calculated this part. We know what this part is. At least we have calculated the P0 integral for this part. So we shall just use that expression and then operate with this operator on this thing, and then we can get this SF x minus x prime. This is not working. So let us now see what this SF x minus x prime is. So what we have shown is the following, that S if x minus x prime is equal to I slash plus n bracket x minus x. And we know that we have already seen that delta f x minus x prime is nothing but equal to minus I integral dq t by 2 pi dq dt plus the x0 minus x prime 0 exponential minus I p dot x minus x prime plus theta x prime 0 minus x0 I. So we have already derived this result earlier. We shall now use this result. Okay. So what we shall now do is act this expression. We have this expression, we shall operate this operator on this expression is important. Therefore, SS x minus x prime is basically equal to. So what? Let us do this thing. Instead of calculating this thing, let us calculate I del slash delta f x minus x prime. Let us calculate this thing. So that is equal to, so this I and this minus I will give me plus 1. Therefore, what we shall have is dq p by this factor that we have, the denominator. So we have this factor, and then this operator del slash will act on these terms. So when del slash acts on this one, on the theta function, we have a delta t minus t prime. Basically, this x naught is t, and this is t prime. So this will give me a delta function, right? So I think I made a mistake. Let's be careful about it. You should remember that this del slash is basically gamma mu del mu. This gamma mu del mu. Okay. So there will be two terms, I suppose. Just okay. So del slash acting, del slash will act on this term, then this term, and so on. So when del slash acts on this term, so let me write it over here. Del slash acting on theta t minus t prime. This is what? This is gamma mu del mu theta t minus t prime. Okay. But this is equal to gamma 0 del 0 theta t minus t prime. And there is another part which is gamma I del I, but gamma I del I acting on theta will be 0. So that is not there. Therefore, we have this will be gamma 0 delta t minus t prime. Then we have e to the power minus I this term. So that takes care of the first term. The second term is plus theta t minus t prime del slash acting on e to the power of minus I t dot x minus x square. So these are the first two terms. Thus, when del slash acts on this term, is similar to the first case. We will get minus gamma 0 delta t prime minus t, because now it is there is t prime theta t prime minus t. So when del t acts on that, we get a minus of Dirac delta function. That gives us e to the power of I t dot x minus x prime. And then the last term is plus theta t prime minus t del slash that completes this thing. From here we can immediately see if del slash, when del slash is acting on this term, you can now replace this del slash by minus I p slash, right? And this del slash by plus I p slash. Okay. Now let us look at the first and third terms. So what we have is gamma 0 delta t minus t prime to the power of this plus the minus gamma 0 delta t prime minus t to the power of. So here what we can do is we can now expand this thing. This will be t minus t prime. We expand the exponential, we get one term as I minus I t0 t minus t prime, and the other term will be e to the power of I t vector dot x minus x prime vector. I think that sign is correct. So, and the second term will be similar, but before writing the second term, I will write down. I will just simplify this term. You can see delta t minus t prime and we have this term. So this is basically 1. You can enforce the Dirac delta function. So that is gone. The second term also you will have a similar thing. So we have gamma 0 delta t minus t prime exponential minus r t vector dot x minus. So that is what we shall have. And now you have an integral over d cube p. So what you can do in the second term or in the first term as you wish. Huh? T prime minus. This is no, this is not T prime minus. This is Dirac delta function, so it is symmetry. You can write it anyway. But the minus sign is crucial because it is coming into the derivative on the theta function. The theta function is T prime minus. So now what you can do is in this p integral, you should remember that this has a p integral, overall p integral. Right? So there is a p integral. What you can do is you can take t goes to minus t in any of the terms. Suppose in the second term we take p goes to minus p. So if p goes to minus p, d cube p remains unchanged, but this becomes a plus. Because if this term becomes e to the power of I p x dot x. Right? And now you can see that this term and this term therefore cancels, and it is zero. So what we have shown is this and this term has cancelled. Is this clear? Are you okay with it?
Yes, sir.
Okay, good. So finally, we have here the following expression. what we have is I plus such this, and therefore now you can basically add this plus n here. If you add plus n, then what is going to happen is the following. Okay, so let me just simplify this term carefully. So this will be equal to. So let me remove this for the time, otherwise confusing. What we have is the following. You can write this expression as minus I. You can take this minus I common. So we will have dq3 divided by this factor that we have in the denominator. Then we will have theta t minus t prime t slash exponential minus ip. Here you should always remember that this P4 vector, we have 4 components P0, but they are not independent of each other. This I mentioned earlier also. P0 is basically related to P vector, even though we write it in this way, in the 4 vector notation. Plus we have theta T prime minus T e to the power I P dot x minus x. This is what here I will get a minus, right? Minus is. So I've taken the minus I common, so I get this. And now what we can do is we can add this minus n, a plus n, add this plus n over here. So what this will do is nothing but simply give us a p slash plus n over here. This plus n, so this comes as a plus n. Because in front of delta f, you have this minus I already. Remember, just recall the expression for delta f, you have this minus n. So when you multiply delta f by n, this minus comes out common. So just the plus n enters this expression. And for this, you have minus p slash minus n. So this minus and this minus gives you the plus n. So your full expression is of this form. So let us write this carefully now. So what we have is the following. S if x minus x prime, that is equal to minus I equal to 2 q t t minus t prime t slash plus n this minus minus t t slash minus f. So this is the expression that we were after. We finally have the expression for Sfx minus x prime, where we have performed the T0 integral, and we have expression in terms of dq, p, and now you can go ahead and you can try and perform the integral over T vector. So there are three integrals, separate integrals now. Integrals over Tx, Ty, and Tz. So you can try and perform that integral. So what you will do, you will go to spherical polar coordinates and try to do this integral. You can try and do that, but we shall not do it now. for our purpose, this expression is sufficient. We want to show now an important result. The important result that we want to show is the following. Remember that in case of scalar fields, we have seen that I delta f x minus x prime, which are the expression for which I have written on the other side of the board. This was basically the vacuum expectation value. So this was basically the VV. So we shall use the short form for vacuum expectation value VV. So this scalar field propagator was basically the VV of this time order product of pi x, and this. So this was the result that we have already seen earlier. And the question is, what is this propagator? Is there an analogous relation for this propagator also in terms of vacuum expectation value of fermionic of time order product of fermionic fields? So this is the question that we should ask, and you can now understand, or you can basically see what it should be. This propagator should basically be the vacuum expectation value of the time order product of two fermionic fields here. But for that, what we need to show is, or what we need to define first, is what is the time order product of two fermionic operators. So this is what we need to define. So we can actually remove this part.
Sir, what is VEV?
VV is vacuum.
Okay, okay.
And this vacuum, you remember, you should recall that this vacuum, see, the discussion that we have been carrying out so far is for free fields. So whenever we are talking, all this discussion of propagator is once again for free fields, and you can understand that we have again switched over from the interacting fields to the free fields case in order to discuss the propagator for fermionic fields. So here there is no ambiguity about what this vacuum is. This vacuum is the state of minimum energy for the free Hamiltonians, because we only have the free Hamiltonian there. But in case of interacting fields, this vacuum can be a full interacting vacuum, that is the state of minimum energy, time independent eigenstate, or the full Hamiltonian, interacting Hamiltonian, or this vacuum can be the vacuum of the free Hamiltonian also. So, but since we are not discussing interactions, so this is the vacuum for the free Hamiltonian. So now, what we shall do is, we shall define the time ordered product of two fermionic operators. So this is the time ordered product, and this is equal to psi alpha x psi bar beta prime. So this is by definition. This is how we define the time ordering. This is for x0 greater than 0, or t greater than t prime. And for the other case, for t prime greater than t, this is psi bar beta prime psi alpha x or prime 0 is 0. But with the difference, this is exactly the same as we had for real scalar fields or complex scalar fields, but with the difference, in case of harmonic fields, we have a minus sign in front. So when this time x0, x prime 0 is greater than this time x0, then obviously time ordering says that the operator which is at a later time should appear on the left, right? So this appears on the left, but you need to switch it over. You need to swap it over a fermionic field, and that gives you a minus sign, because fermionic operators are anti-commutative, therefore you have this minus sign. So this is the definition of the time ordering for fermionic fields. And now what we need to show is that, or we need to calculate the following. We need to calculate psi x, psi bar prime. You can put the labels alpha and beta because these are spin-offs, so these are like columns and this is a transpose. This object has one column and four rows. This has one row and four columns. So you can put the labels alpha and beta, but just to avoid these subtleties, instead of putting labels, you can put it if you wish. So let us now calculate this object. So we need to calculate this object. So in order to calculate this object, what we need to do is the following. We need to write down more expansions for this thing. So you can keep the time only outside, or you can basically write this now as gra 0 theta t minus t prime psi x bar prime, then minus theta t prime psi bar x x. So we have expanded this time ordering now. X. So that is what we have. And now you can substitute the mode expansions here. So you have psi and psi bar. So this is a little bit, right, many things, a little bit tedious. So what we need to do is the following. You remember what psi of x is. Psi of x is 2p by this. Then we have a summation over spin ds p. Then we have this USP spin on the Dirac spin on in momentum space. Then we have e to the power minus I x plus d dagger ESP to the power I. This is what we have. And similarly, psi bar, you can get psi bar from here, and then what we need to do is multiply both psi and psi bar. And if you do that multiplication, it's a bit. To do that multiplication, so let me just write it short here. Psi with psi bar to be something of its form b plus e dagger e to d. And then we have for psi bar, we have b dagger u bar plus e. That is what we should have. If you multiply this will give us b dagger u bar plus b dagger e u bar plus b D dagger, D, D, right? So when you multiply psi with psi bar, you will get these four terms. Now you can immediately see that this term, because there are this D dagger and D dagger, and you have kept 0, 0. So this term is 0. Because it will be B dagger will do what? B dagger will create an electron, D dagger will create a positron. So on the right hand side we have one electron, one positron. On the left hand side we have no particles, so it will be 0. Similarly for this term, this will straight away annihilate the vacuum. So this is gone. This will also annihilate the vacuum. Because you have D sitting on the right. And therefore it kills the vacuum, it gives you 0. So only term which contributes in psi bar is D dagger. Nothing else. So you can basically simplify this. So you have theta simplify. So this will be dq dq times by 2 pi whole cube 2 square root of dp dq prime. Okay. And then we shall have times. We have this summation of s prime b s e dagger s prime prime s p u bar s prime.
Sir,
Yes.
why the D dagger B dagger term vanishes?
Which term?
D dagger B dagger.
D dagger, B dagger. Okay. So let us. I am writing over here. Okay.
Okay, sir.
So you have something like this.
Yes, sir.
What will B dagger do?
Okay, okay.
We create an electron. What will B dagger do?
Get and positive.
Create a positron. So what is this state?
0. Yeah.
Okay. So this gives us this term. Let me see if I missed anything. I think I have missed something. I missed the exponential factors. So let me write down the exponential. This will be okay. So you should remember that you have a vacuum expectation value. This is like this, right? So you have this thing, and then we have e to the power of minus I t dot x, then e to the power of plus I, because it's I bar t prime. That completes at least the first term, and then you will have a similar. I'm writing this dot dot dot. You have a similar term for this second term. Now, for this term, you can immediately see that if you use the anti-commutation relation for B and B dagger operators, that will give us what? This will give us basically delta, canonical delta, S prime, and Dirac delta function T minus T prime. I'm just doing the first term, the first. So canonical delta over the spin basically gets rid of one of the summations. So this is one. And the Dirac delta, what it will do, it will keep one of the integrals, momentum integrals. So you can do one of the momentum integrals, that is 1, and this becomes 2 EP. There is only one momentum integral now. Canonical delta is 1, Dirac delta function is 1. So we have used the. I will change it. I will change it. So now this P prime will become P, and this will also become. And therefore, what we have now is the following. have basically P minus P prime, or sorry, this is I P dot x minus x prime, right? And also this P is S prime is S. So this is also. So this is the first term, this term here. This term basically gives this thing. You can do the same thing for psi bar psi. And in psi bar psi, in case of psi bar psi, you will see that you will get the d dagger term. This was with d dagger. There you will have the d dagger term. So you have this. Now what you can do is the summation over S USP over SP, and you can now perform the spin sum. You have already learned in the course on relativistic quantum mechanics. This basically gives us the factor of P slash. So what we have done is we have used the result summation over S USP U bar SP basically P slash. When you do it for the V spinors, first of all you have this minus sign in front. When you perform this sum over the V spinner, the sum over the spin for the V spinners, you get E slash minus M. Therefore, you can now see that this object that you have is basically nothing but this is nothing but ISF. We have today we have shown, we have completed the Dirac propagator. Propagator for Dirac fields, for free Dirac fields. Let me mention this is free. Everything is free here. No interactions here. It's a propagator for free Dirac fields, and we have shown that the propagator, the Feynman propagator for this I times the Feynman propagator is basically nothing but the VV or time order product of two fermionic fields. And you can, so this is a very important result for free Dirac fields. And you can convince yourself that if had you calculated, suppose you calculate this thing, psi bar time order product of psi bar psi, right? Then in that case you just get a minus sign. Everything will remain unchanged, but you just get a minus sign. You can convince another thing, you can just check it for yourself that if you had you calculated psi x prime, psi x prime, no bar, that will be 0. Because these are anti-commuting. For Dirac fields, these are anti-commuting fields. So psi or psi bar, this is 0. This is something you can check it for yourself. So the propagator for the result for SF, you get it only time ordering of psi with psi bar. So what we shall do, so we have completed the propagator theory of this propagator for free Dirac fields. What we shall do in the next discussion is we shall look into the propagator for gauge fields, for the electromagnetic field. So let us stop here today and continue on Wednesday from this point.
Sir,
Yes.
I have a question from the previous class actually. So when you are doing the fish diagram and we are calculating from the amplitude, second order amplitude. So when you substituted the value of the Feynman propagator, we know that Feynman propagator is even function. I mean, we can delta f of minus x is delta f of x. So when we use the form of in the momentum space integral over d4k by 2 pi whole to the power 4 exponential of I k dot x minus y by k square minus m square plus I epsilon. So we can either use e to the power plus I k dot x minus y or e to the power minus I k dot x minus y. Both will give us the same answer.
Both will give you the same answer. Absolutely.
But there I could not find the same answer actually.
Oh, I intentionally, or yes, you are right. Who is this speaking? Is this Somabroto?
Yes, sir.
Okay. So see, I intentionally, when I wrote down the expression for the fish diagram, so using the Feynman rules in position space as well as the rules in the momentum space, I intentionally wrote it down as for the I delta f x minus x prime, I wrote it down as e to the power of, in the momentum space, as e to the power of I p dot x minus x prime. I could have written down as e to the power of minus I p dot x minus x prime. That also I could have done, but I have intentionally not done it for this very simple reason, is that the following reason. The reason goes as follows. If you have this kind of a diagram, suppose I call this vertex as y, this vertex as w. So this is one leg, momentum p1, this is momentum p2, this is q1, this is momentum q2. So when I'm using this, when I'm writing the external leg for this, I'm writing e to the power minus I p1 dot y. And when this is going out, I'm writing it as e to the power of I q dot w. So you can see this is going out, this is the time direction. So if I just separate it by planes, so when it is going up, from this line is on the upper side of this line of this plane, and this line is on the lower side. So on the lower side, I'm using this plane wave, so that is the incoming one. For this is the outgoing plane, the outgoing wave, so I am using plus sign. And for this propagator, you will see that I have used, if this is the momentum k, there is only one loop momentum, so this gives, you have I delta f y minus w. So I'm taking this as y and this as w. And when I'm Fourier transforming this, I'm writing this as e to the power of I k dot y minus w. Why did I do that? I did it because, see, this line is on the upper side of this plane, therefore I put the ik plus ik dot y. But this line, when it enters this, it is on the lower side of this plane. So I am using e to the power of ik minus ik dot w. That is the reason I used it in this way. But you are absolutely right. If I used e to the power of minus also, minus ik y dot minus ik y minus w, then also you will get the same result. But you should check it for yourself. I will not do it for you. It is very simple.
Yeah.
You have to just make certain transformations like k going to minus k or q going to minus q, and you will get k, mainly k going to minus k. If you do that transformation, you will get the result. Immediately you will get it. There will be no problem. So you just do it, try yourself, you will get the answer. But I intentionally use this thing in this form so that you don't fall into that trap. So when you put a minus sign, you problem which you have encountered, I also encountered the same problem, but you can still do it. That is not a problem.
Okay, sir.
Okay.